Okay. Question number 2.254. Find the temperature distribution in the space between two coaxial cylinders of radius R1 and R2 filled with uniform heat conducting substance if the temperature of the cylinder are constant and are equals to T1 and T2. So in this question we have a cylinder. Let's assume that length of this conducting cylinder is L. So it is coaxial in nature. This length is L. Inner radius is R1. Outer radius is R2. This inner surface is placed at temperature T1 and outer surface is placed at temperature T2. So we have to find out temperature distribution within this material. So let's assume that conductivity of this material is K. Okay. So we need to write the expression for temperature. So for that, let me draw the cross-sectional view, that is top view of the cylinder. That this radius R1, radius R2, temperature is T1 and temperature T2. Suppose if we'll move forward and we'll cut a small strip here at any distance R. This is at any distance R, the width of this strip is dr. So we can write expression for heat conduction, that rate of heat flow dq over dt is equals to minus Ka dt over dr, because in this case this width is dr, right? So because here variation in r, so we need to put expression for this area, because as we move further, then area of the surface, the cross section for the heat flow would change. How it is changing? The circular range of the cylinder, because there will be a formation of cylinder at each step if you look into 3D. So this is 2 pi r and length is L. So this area can be replaced by K into 2 pi r into L into dt over dr, and this rate of flow is of course constant, so we can put it as constant C. Okay, so from here we can write that constant C is equals to minus 2 pi K into L, nothing is changing out of these parameters, into dt over dr and r. So it's up to you that we can take this entire value as a constant for the simplification. Okay, or we can continue with it. So let's continue with it. So we can write dr over r into C is equals to minus 2 pi k into L into dt. So now we need to integrate. When radius was R1, so the temperature is T1. For radius, any general value R, let's assume temperature is T. So for this integration, we can write C into ln R over R1 is equals to minus 2 pi KL into T minus T1. Okay. Now see. So we can calculate expression for T, of course, that T is equals to C upon 2 pi K into L. Okay. And if we'll multiply the negative sign here, then we can write ln R1 upon R plus T. Okay. This is the final expression. Now see. We can replace this entire term as a constant. Let's take constant A. So let me write this equation again. This is T equals to A into ln R1 over R plus T1. Okay. Still, this constant is not known, right? So we can put some boundary condition that when R is equals to R2 at outer surface, then temperature T is equals to T2. Okay, so we can substitute this condition. We can write T2 is equals to A into ln R1 over R2 plus T1, right? So from here we'll get A equals to T2 minus T1 over ln R1 over R2. So this constant can be substituted here, and we can write the final expression for temperature by putting in equation of T. Then T is equals to T2 minus T1 over ln R1 over R2 and total into ln R1 over R plus T1. So this is final expression how temperature is changing. Even if you notice this, then R2 is greater than R1, so there would be negative sign, so you can write minus R2 over R1 for your verification, and this temperature will reduce as heat flows from higher temperature to lower temperature. So no need to get confused that this temperature is increasing. This is not increasing because in denominator there is R1 over R2 and it will introduce a negative sign here. Okay.